Got that.
It's so hot. It doesn't seem...
This is Doug, Spencer, and Han's AP Physics project. We will address the tension and aeroelastic flutter in slacklining.
So this is the tension portion of slacklining. Slacklining is when you have a line connected between two trees at equal heights. And then when you step on the line, you create tension in the line on both sides. Today we will solve for the tension on both sides of the rope. So in this case, this would be basically what slacklining is. So this line is when the slackline is completely slack and there's no one on the line. Once you step on the line, as long as you're not in the center, there's going to be tension on this side of the rope, and not tension on this side of the rope. In this case, Doug is closer to this tree, so this angle is going to be bigger than this angle. We're going to approximate this angle to be 20 degrees and this one to be 30 degrees. So then, in this case, because he's at equilibrium, the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. So then, if we draw a force diagram, we would see he has the force of gravity pulling down, which is mg, and then he has this rope going this way, and then this rope pulling this way. Where you have theta 1, theta 2, t1, and t2. So then your sum of the forces in the x direction would be equal to the cosine. It would just be the x component of t1 and the x component of t2 summed up. Then you would have cosine theta 1, sorry, t1, plus t2 cosine theta 2, and all this equals 0. So that's how you do one. And then the sum of the forces in the y direction would be negative mg, because it's going down, plus t1 sine theta 1 plus t2 sine theta 2. And then if you use the first equation to solve for t1 in terms of t2, let's say, you'll get t1 equals t2 cosine theta 2 divided by cosine theta 1. In this case, we approximated cosine or theta 1 to be 30 degrees and theta 2 to be 20 degrees. And then if you plug this into your other equation, you get mg equals t2 cosine theta 2 over cosine theta 1 plus t2 sine theta 2. Doug weighs about 175 pounds, which is about 800 newtons of force pulling down due to gravity. So then when you plug everything in, you get T2, whatever this was, which is a number. So then you got T2 equals about 904.4 newtons. And you plug this back into there, you get T1 equals 981.38 newtons. So then you can see that T1 is going to be greater than T2. So the force, or the tension between on the string for the tree that's closer to Doug is greater. So this tree is doing more work than this tree is to hold Doug up so he doesn't fall.
What you see here is the oscillation of the slackline due to wind traveling perpendicular to its length. This phenomenon is called aeroelastic flutter. It is the result of wind applying a force on the line and tension counteracting this force, only to cause the slackline to rotate back and forth with increasing intensity, or amplitude if we consider it as a wave. In this freeze frame, we can see that the wind hitting the slackline would cause the line to rotate counterclockwise. As tension overpowers the force of the wind, the line swings back, and the wind can now cause the line to rotate clockwise. Although some claim it to have been the result of resonance, The bridge of the Tacoma Narrows, as shown here, actually collapsed due to the same phenomenon as seen with the slackline, called aeroelastic flutter. The wind continued to transfer energy to the oscillation of the bridge until it finally collapsed.